It is now 5:01, and we will be officially beginning our Aquaphotomics Christmas special. I'm very glad to see you all here. So for the beginning, I just have a few information for all of us. First, a quick agenda. After my introduction, I will announce Professor Tsenko, who will give you some information about the past year and some surprises that will be waiting for you during the course of webinar. And then she will announce the star of today's webinar, Dr. Alexander Mallett from France, who is going to give us a very interesting lecture about how to remove the water effects. And during the entire webinar, you have available English transcript. You can put it whenever you choose. The lecture of Dr. Mallet is going to be translated, so it will have subtitle in Japanese. If you experience any trouble with transcripts or with whatever Zoom features, please feel free to contact host and ask for help. And one more thing, during the entire lecture, during the entire webinar, please feel free to type your questions or thoughts in the chat box. And after the lecture finishes, we will, together with host Professor Tsenkova and the lecturer Dr. Mallet, we will take care of all these questions. And I hope to have a very nice discussion on all these points. So without further ado, welcome to Aquaphotomics Christmas Special, the first webinar in the series of 2 webinars. And I will now introduce Professor Tsenkova. Please give us some introduction about this year.
Okay, thank you very much, Elena. I just want to share my screen. And I cannot. All right. Okay. First of all, very happy to thank you for opening, Yelena, of the first such event that we have in our Aquaphotomics Society. Our Christmas webinar, our first webinar. I'm very happy that we finally could make it. Congratulations to all the organizers of this webinar. Thank you, Lawrence. Thank you, Elena. Thank you, everybody for preparing this webinar. Thank you very much, Alex and Pierre, agreeing to do the webinar. Recently, I've got an inspiration about the new name, not new name, a translation of Aquaphotomics in Japanese. So, you know, water and light, and the third Japanese character means the way of living. So it's, and in hiragana, it is pronounced like mikodo. There is a story about this. So mi is a polite way of saying something very polite. So in the past, mi kage meant emperor. So mi is a very polite way of saying something about light as a sound, but as a meaning, it's all, and do is a way of living. So this is my Christmas present for you. Now, we have, well, the screen is not shared. Yelena, can you hear me? Yes. Is the screen shared?
It is not in full view.
It's not in full view.
Yes.
Okay. How about this? Now, did you get the full view?
Yes. 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 Thank you.
Okay. Thank you. Okay. So I just wanted to tell everybody how happy I am that we have 88 participants in this webinar. We didn't have very long time to prepare and to announce, but for that short time of a little bit more than a month, I think. If I'm not correct, Ilana, please correct me.
Shorter.
Shorter, even shorter. So we have 88 people from 18 countries, which is absolutely amazing, I think. Because we have so many participants from Japan, we decided to do translation in Japanese of Mallet's presentation, because he was so kind to send us his presentation ahead, so we could have some time to prepare this. For the second webinar, it will be difficult, maybe because we don't have enough time. But it is our first exercise. So please give us later on feedback about the Japanese, how was it helpful, and we will try to do this in the future as well. Now, a good news, so I'll go this time with maybe for people that are newcomers. What I would like to say is that this time we don't have much time to talk about aquaphotomics in details, what exactly aquaphotomics is. But I'm sure you have been to our website, you have read our papers, learn about aquaphotomics, and we'll have many other chances to talk about this. This Christmas webinar, I decided to share with you our news, because we have met in March for our fourth international conference of aquaphotomics in Kobe, Japan. Meanwhile, what happened is the following. Our first book on aquaphotomics is already just a few weeks ago out. It is published by Springer, and we wrote this book with Jelena. It shows the road from biodiagnostics done with near-infrared spectroscopy that actually showed us the importance of the water absorbance in a living system, and opened my eyes to look at the water and how the neglected for so long time, even now, by spectroscopy, water as being a very strong absorber. Usually people just omit it, neglect it, think of water as something that is obstacle. And but you will see in the presentation of Alex today, so he also wants to get rid of the influence of the water. That's why he wants to study water. Well, as a kind of joke, I can tell you that you cannot get rid of the water, but by knowing, having a knowledge about water, you know how to deal with and how to get information from the water. And this is what aquaphotomics is all about. Water is the source, is the universal sensor in, I would say, on Earth, in space. So we can get lots of information from the water, as water works as a mirror, not only regarding the visible light, but all the energy. And the water is the only absorber, the only substance, organism, I would say. In Japanese, I would say sonzai, something that is living, that absorbs all possible energy. So that's why there is no way that you can get rid of absorbance of energy from the water. On the other side, this is the most desirable source of energy that we at the moment, we need this kind of sources of energy, of course. And we have to be very careful about, very knowledgeable about it. That's my point. So you can purchase, or you can contact us. You can read separate chapters of this book. And Jelena asked me to tell you, shall I say what we decided? That we're giving away oh, Yelena, oh, you are going to say it at the end, right? Okay. So another news, we didn't know that we were again so busy. After the conference, we wanted to get rest, but that never happens. So we have a special issue on aquaphotomics in molecules. So the deadline was December 15, but if you're very much willing to give a paper and try, you can try. You can still really try, I think. So, well, we have to announce now. Yeah, Elena did it, but with a little bit more details, I can tell you that what happened at the conference, I gave my final lecture as a professor at Kobe University in Japan, because I was supposed to retire. So I did not retire. But I continue working as a specially appointed professor in newly developed department. So we established an aquaphotomics research department at Kobe University. And this is where Elena is specially appointed assistant professor. And we expect postdoctoral researchers to come and work with us. So there is always vacancies. If you're willing to come, you're very welcome to come and work with us. So we have also an announcement to make regarding, we have an open position for postdoc in the lab for a person who can speak Japanese and who can freely use Japanese. It is very difficult in Japan to do research without knowing the language. So this is a very important requirement. I have in the chat questions about what happened to my Japanese translation. I hope that Lawrence can do something. Or because it doesn't go like this, so we can go. I can go in Japanese now. Yes. ちょっと日本語でいきます。日本語のトランスレーション、今、確かおっしゃる通りできなかったので、日本語でいきます。ウェビナーにようこそ。今年、国際学会3月やって、やってから初めての、の経験ですけれども、まあ、わかるように、ちょっとまだ難しいところがあると思いますけれども、まあ、そのうちに多分経験積んで良くなると思います。で、いくつかのアナウンスメントを、Yelena, can we put some subtitles in Japanese on while I'm speaking, or that was impossible? No. Okay, understood. Thank you. I'll continue in Japanese then, just for a few minutes. で、今、今回のウェビナーが2人の15日と22日のウェビナー2回やります。で、最初はマレット・アレクサンダーがフランスの方、神戸大学の研究室、何ヶ月ぐらい研究されて、とても今日のウェビナーのテーマがとても面白いと思います。もう一つはオーストリアの方、自分で発表された学会で発表されて時間が足りなくて、もっと時間をいただきたいということで、22日ライブでウェビナーをします。あと、その国際学会から今までの間何が起こったかというと、 4月1日から神戸大学の新しいアクアフォトミクス分野、研究分野できました。でそこが、私、神戸大学の、教授から、今度、神戸大学の特命教授になって、イェレナで特命助教になって、で、これからポスドクの方々が、ぜひ研究室に来られたらどうかと、応募してます。あと、アクフォトミクスの細かい、今回は具体的な話は、多分みんな、ウェビナーに来られた、参加されている方々が、ウェブサイト、2つのウェブサイト、今みんな見ていらっしゃるウェブサイトが、神戸大学のアクフォトミクス研究分野のウェブサイトですね。で、あそこからすぐお分かりになると思いますので、いろんな分野の論文、今年の論文がすごく増えた。予測したのは今年は182の論文が出る予測なので、今の段階で179論文がもう出てます。だからとても嬉しいのでそのニュースをシェアしたかった。でもう一つは最初の本が出ました。アクフォトミクスの英語ですけれども、そのアクフォトミクスのアイディア、だから私の研究、牛の病気の、だから乳牛の病気の診断、近赤でやったらその水の役割を見えてきましたので、そこからどういうふうにアクフォトミクスが生まれてきましたっていうストーリーが見えますので、ぜひ本も手に入れていただいたら多分そのストーリーがわかると思いますし、チャプターそれぞれのチャプターが必要であればまたコンタクト取っていただいてまた注文できると思います。まあちょっと長くなったのでその時間超えてるのでもうこれぐらいで今日みんな88人の参加者18カ国の参加者本当にようこそ今日楽しく最初のウェビナー過ごしましょう。ありがとうございます。Yelena, thank you very much. So this is what I have to say, and now we can go to Alex.
Okay, so Alex, are you ready?
Yes.
Yes.
Yes,
okay.
I'm ready. Yeah.
Just for all of Japanese people who are attending the webinar, there will be now a subtitle with the lecture. And please type your questions in the chat box and don't leave immediately after the lecture finishes. Stay, we will have a discussion. And just two more important things to say. We will be giving as a present one book today and one book next webinar to randomly chosen one person from the audience. So stay here to give us address. So we will be saying after the lecture finishes who won the book. And please complete, there will be like a short questionnaire with 3 questions to just say what you felt about the webinar. So Alex, thank you very much for waiting. We can now start.
I'm very happy today to present to you my PhD work entitled Near-Infrared Spectroscopy Applied to Solid Organic Waste and How to Avoid Water Effects. So the PhD work was under the direction of Jean-Michel Roger and Jean-Philippe Steyer and co-supervised by Eric Letry, Riyad Bendoula, and Cyril Charnier. And so it was a joint research project between two partners, so INRAE with 2 institutes, so the Laboratory of Biotechnology for Environment in Narbonne and the ITAP unit, the Mixed Unit Research ITAP in Montpellier. So this is the agenda I will follow. I will first start with an introduction on the context of this PhD work, present to you my scientific objectives, and then I will present my materials and methods which I've used to answer those scientific objectives. I will go through 4 main results that I've selected to present to you today, and we'll go through conclusions and give some perspectives about the work. So as an introduction, the context is on anaerobic co-digestion process. So we see that we have a variety of inputs, including biowaste, crop residues, urban and industrial effluents, a wide diversity of substrates, which can be valorized through the anaerobic digestion process to provide different outputs. So we have the biogas itself, which is mainly made of CH4, methane, and the digestate, which is the co-product. And from those outputs, the biogas is usually transformed to with combined heat power to produce both heat and electricity. And more we have gas grid injection, so we directly inject the gas in the gas grid, and we can also convert this biogas into vehicle fuel. And the co-product, the digestate, can be really used as a fertilizer in agriculture. But in this process, we see that those inputs can be very diverse. We have they are very highly diverse, both in terms of biochemical properties and physical properties. And more than that, we have some daily fluctuations of both in terms of quality and quantity. And so this poses some questions on how to optimize the process, and in particular, how to optimize the feeding recipe, in which proportions we're going to put those inputs on a daily basis. And we see that it requires, therefore, fast and reliable characterization tools in order to characterize those substrates on a daily and continuous basis. So in terms of substrate characterization, the main characteristic that is actually today monitored and used to optimize the feeding recipe is the biochemical methane potential, so BMP. So it consists in taking the organic waste and putting it into glass vials with an inoculum. And during 30 to 60 days, we're going to let the anaerobic digestion process go through. And we're going to monitor the gas production during the degradation process. And the accumulated volume that we have measured of gas corresponds to the maximum volume of gas that can be extracted from a substrate in optimal conditions. But we see that this process is quite long. It takes from 30 to 60 days, depending on the substrate. And so, since about 10 years ago, the LBE with ETAP and also another company called Untitled have developed and proposed the nears-based characterization tool. And today, this is actually used by BioNTech and proposed as a service. So those substrates are prepared. We have freeze drying and grinding steps. Then the powder that we obtain is analyzed through spectroscopy, near-infrared spectroscopy in reflectance mode. And through chemometrics, we are able to predict the methane potential. So that was the results of the first thesis of a PhD by Lester et al. And then a second PhD actually extended this characterization to other characteristics, including proteins, lipids, carbohydrates. And so we see now that we have a full description of our substrates, so we are able to optimize the feeding recipe. So, but unfortunately, well, I will go through what are the current hurdles. But before the advantages, we see that we have a fast measurement, like most of the near-infrared spectroscopic applications. Instead of 1 to 2 months, we do it in 4 days. It's applicable on a very highly diverse range of waste. It's accurate and reproducible, and it's now possible to optimize the feeding recipe, the strategy. But the hurdles is that in this process, what really takes time is the sample preparation. The near-infrared spectroscopy takes about 5 to 10 minutes, but it In fact, the freeze drying and grinding steps take up to 4 days because we need to send the sample to the laboratory and then do the freeze drying. So we have to freeze it, then dry it, and it takes 4 days. So why do we do that? The sample preparation today is required to avoid the particle size effects and the water effects. So it's a time-consuming steps, and one of the drawback of this technology is that there's a loss of volatile fraction during the drying, and in fact, in anaerobic digestion process, it's quite important because the volatile fatty acids, for example, can account for a major part of the VMP, the potential, the methane potential. And so it limits the online applications to have a continuous analysis of the substrates. So my operational context is really this one: how can we avoid the freeze drying steps and analyze the fresh matter directly by near-infrared spectroscopy? So there are two underlying questions. The first one was, can we find modeling strategies that can account for those moisture content effects? And the second one is, are handheld current portable spectrometers, are they suitable for characterizing such a diverse city of organic waste and when they are wet? So this part I didn't, I decided not to present to you today, but we have worked on this during the PhD work. So in terms of potential applications, what we foresee is online analysis. So we have in front of at the entrance of the digester, we have an online analysis of all the feedstock, or on-site analysis where we have portable spectrometers and people analyzing the different organic waste sources. So to answer this question of how to build a robust model against water effects, the first question that we've asked ourselves was whether we could influence the influencing factor, control the influencing factor. So that's actually what we're doing today. We're freeze drying and grinding, and so we reduce the influence of water and particle size. But if we don't want this, then one of the second question is whether the measurement method itself can be changed in order to be less influenced by the influencing factor. So when we think of the measurement mode, we have different, when we send light on a substrate, depending on where we actually collect the light, we will have different photons with different information. And so the resulting spectra that we measure is going to be more or less influenced by the water effects. And finally, the last question is whether the model pipeline itself can be influenced, less influenced by the factor. So that's the whole world of chemometrics and preprocessing. So my scientific objectives were the following one: to develop a better understanding of moisture content effects on NIRS applied to a wide range of organic materials. And the second objective was to find new ways of building models that are more robust to moisture content effects. So now I will present my materials and methods that we've developed to answer those questions. So actually we developed an innovative system that allowed us to collect the spectral variations that were related to water variations. So both to actually evaluate what are the moisture content effects, but also to test some new methods to build models. So it consisted of a closed circuit with an air drying. It's an air drying system where air is actually dried by a desiccant, and through the dried air, the sample can be dried along in about two to 3 days, depending on the substrate. And along the drying, we actually collected, thanks to near-infrared, we collected spectra from under the sample. And the desiccant was also weighed in order to evaluate the loss on dry, so the amount of water that was extracted. And so from this, we could actually estimate the dry matter of the sample with its spectra. So this is the kind of data set that we obtained for one substrate. So here we can see in blue that we have our wet spectra, which is with the two main OH absorption peaks. And then along drying, so from 1 to 3 days, we end up with a spectra of a dry sample in red. So we did this actually for 89 substrates, covering a really wide range of biochemical and physical composition. And we obtained more than 120,000 spectra. And this covered a very wide range of the full range actually of dry matter. And in parallel, all of those substrates were freeze-dried and ground with the current process, ER-scan, to obtain the full description of our substrates. So just to give you an example of the complexity of this data set and the wide range of the physical properties and biochemical composition, we have solids, we have liquids, we have translucent liquids, suspensions, emulsions. It really covers the type of organic waste that is susceptible to appear in a digester. So one of the first tests and studies that we did was whether we could actually build a model with this data set. So the aim was to evaluate global correction methods that exist today in chemometrics to account for moisture content variations. And so it's the approach, one model for all substrates, all dry matter range that we evaluated. So we tested this for BMP prediction, which is really the main characteristic that is that needs to be monitored. So the workflow was the following. We have an original BMP dry model, which worked on freeze-dried and ground samples. And then we have our drying experiments with spectra covering different moisture contents. And our aim was to build a BMP wet model, which worked on raw and wet samples. So the methods that we evaluated were the following ones. We have methods that were more on that worked more on the spectra, trying to correct the spectra and reduce the footprint of water. And other methods which were more on the model itself, trying to build a new model. And, so the first ones are more on the spectra, so feature selection. It's a very simple method where we from knowledge, we know that in some regions of the spectra, we absorb water, the OH bands absorb. So we just cut those water bands and try to build a model. The second one was scaling or skewing. The principle is really to downweigh those regions in which we know that the moisture content makes the spectra vary a lot. The second one is quite similar, but it uses an orthogonal projection. So we define, we identify the subspace that of the moisture content variations, and then we project orthogonally to those to this subspace in order so that our spectra will not be influenced by those variations. And OSCE-PO is quite similar, but before identifying the subspace, we project orthogonally to what we are going to actually predict in order to, because probably in those moisture content variations, there might be information related to that could be useful to predict. We also tested the transfer methods, so piecewise direct standardization, which the principle is you build a model between your wet spectra and your dry spectra, a linear model, and then you do a model on the dry spectra. So then the methods were more working on the model itself. The really easiest approach is the model update. So it's also called the data augmentation. The principle is just to combine the wet spectra and the dry spectra together and try to let the PLS find the most best model. A similar method is repeatability file, where instead of adding the wet spectra, we add those differences between dry and wet spectra, and we say that the y, so what we want to predict, equals to 0. And we can also weigh the two data sets, the influence of those two data sets. And then we tested stacking, where the principle was to actually stack all those methods together. The predictions that were made by each of those samples. We did a PLS on those predictions to predict the BMP. And in the hope of really robustifying even more, because we know that each method could have its own bias and performances. So the two data sets we have were the freeze-dried ground samples, so X-dry, that we call X-dry, and the raw samples analyzed during drying, X-wet. And then we splitted those sets into train and test sets. So X-dry train, X-dry test, X-wet train, X-wet test. And here is what we obtained for the original model, which means that it's the model that was built only on the dry spectrum. So here it's the results, so predicted versus observed. What we have in blue is the X-dry train. So then we have the X-dry test. We see that it follows a nice, the identity curve very well, identity line. And now on the X-wet train and X-wet test, so those are the wet spectra, we see that it doesn't work. Our current model, the dry model, doesn't work on wet spectra. So this is what we're going to try to remove, to correct. So the RMSCP, if we look on each time on the test sets, so X-dry test and X-wet test, we see that we have a RMSCP of 65, which is kind of what we aim to have, we target for the MP prediction. And we have 192 of RMSCP, which is really bad, of course, and is not suitable. So now to the right, I present to you one of the correction methods that we employed, so the repeatability file. I will present the others just later. And what we can see is that indeed, in terms of RMSCP, we were able to enhance those performances with a 94 RMSCP, which is quite okay in a sense. But if we look at the R squared, that's where we see that, in fact, we don't really have a model. On the first one, we see that we have a negative R squared, and on the right, with the repeatability file, we see that we only have a R squared of 0.15. And so clearly, there's no model. We can say that there's no model, and that it didn't work. So here are the results that we obtained for all the methods. So my original dry model, which was built on the X-dry set, here are the performances. We see we have about 64 RMSCP, and the R squared is about 0.7, as we have seen before. On the X-wet, we have seen that it's really a bad RMSCP. And what we can see for all those methods is that, in fact, all the R squared are negative or 0 or not above 0.2. So in fact, none of those methods were able to correct and account for moisture content effects. So another point on this study was that the prediction error really depended on substrates. And so here are the RMSCP that were evaluated per substrate, and we see that we really have big differences with substrates which are up to 175 error, and others which are really good under 0.40. So what we thought was that it implied different sensitivities to moisture content effects depending on the substrate type, and also possibly different types in terms of spectrum, different types of moisture content effects that couldn't be counted with one global model. So our conclusion was that we needed to better assess moisture content effects according to those substrate types. So this makes me come to the second part about the non-linearity of water effects. So the objective was really, as I said, to analyze moisture content effects according to substrate type and moisture content level. So to do this, we use the most simple and basic tool of chemometrics, which is principal components analysis. The spectra during drying were projected into the PCA components. So we have the scores, which we looked at the scores depending on both the substrate type and the moisture content level, how they evolved. And of course, we analyzed each of those, the loadings of each principal components to better understand what, in terms of spectra, what kind of variations it represented. So here I've decided to present to you the within substrate variations, PCA on the within substrate variations, meaning that for each substrate we center the block, and then we do a PCA on all of those blocks. So it allows us to really see for one substrate what kind of variations we have during drying. So the first loading here is really corresponds to the kind of the mean spectra. It's a really a general, it represents the scattering mostly. And it explains actually 92% of the variance, which is quite classical in near-infrared spectra. Most of the information is in fact based dependent of scattering. And here I present the scores evolutions with moisture content that we obtained. So what we observed was that we have the PC1 score and the evolutions with moisture content. And so I've just represented some of the substrates. So, and we see that for most samples, we have a decreasing scores during drying. And what we also see is that this evolution is nonlinear. We don't have a linear relationship with moisture content, which could also explain why we have issues to actually predict moisture content itself. So that was the first learning. The second learning was that, in fact, we see that we also have a nonlinearity due to the fact that we have substrates which have opposite evolutions, which are mostly highly fat content substrates, like pork, sour cream, mayonnaise, butter. All those samples actually showed an increased absorption during drying. So we then found out those two nonlinearities, and then if we looked at the second PCA, the second principal components, and we look at the loadings, we really see those two clear OH absorption bands with this explained variance. And when we look at the scores evolution for in this principal component, we also see that, of course, we also have a decrease of those absorption bands as we dry, we have less absorption due to the OH vibrations, and that this evolution is also nonlinear. But in fact, we also found out that some substrates, up to a given moisture content, over a certain moisture content, didn't show up those spectral absorption features. So in fact, at the end of the drying, it indeed showed up a decrease, but up to a certain moisture content, we have a flattening of the spectra. And we interpreted this as being an increased forward scattering. There's no more light that comes back to or very little light that comes back to the detector. And so for all wavelengths, in fact, we can differentiate in terms of absorption the features. So the conclusions were that as we see, the water effects are very complex. They mix chemical effects related to absorption and physical effects related to the scattering. And those effects depend both on substrate type and moisture content level. And we also saw that from here, we really, one of the learning was about the physical effects that I think we don't really think about when we think about water effects. We always talk about those OH absorption bands, but there's a big effect just related to the change of scattering due to water. So we wanted to investigate and better understand these effects. So in this study, that's what we're going to try to answer. The objective was, how does water actually affect the light scattering in the media? And to do this, we wanted to study independently those scattering effects. So from the chemical effects, because there are some interactions, and in order to differentiate those, we tried to find a sample that where we could study independently those effects. So the proposed approach was to find a sample that was a scattering media, a particulate media, with limited chemical interactions, with no solubilization processes or that really add up to nonlinearities, and that we had very limited absorption from the dry mass. And we found this sample, so aluminum simple system consisting of aluminum paper pellets mixed with water. So from under, we still have the measurement from under this the Petri dish. And so to really come back to understand the scattering effects, we have to come back to the principles of near-infrared spectroscopy, so the Buber-Beer-Lambert law framework. So in transmission measurements, we found that, so those three authors found out that the absorbance, which correspond to minus log of the transmittance, was linearly related to the concentration C. So C is the concentration of the absorbing sample, in our case, water. And L is the path length. And so we see that we have this linear relationship. But what we know is that this law, it's like the ideal perfect gas law. It's never really works, but it's a good model to build on. So it holds in very strict conditions: homogeneous and fully transmitting medium, low concentrations, independence of absorbers. If they hide each other, it doesn't work anymore. And the use of monochromatic light. So what happens in scattering media? Because we know we actually can characterize it with reflectance modes and substrates. So how is this dealt? So the light scattering results in two phenomena. The first one is that we have path length modifications. Due to repetitive refraction events, the light actually travels furthermore in matter. And we also have a photons loss. Due to scattering, the photons actually never come back to the detector. They refract, scatter in the media, and never come back to the detector. And so, as a measurement, the absorbance, it's going to be an additive effect due to this photons loss. So, in terms of modeling, what was proposed by Martens et al. Principally, it's at the basis of EMSC preprocessing, was to actually model those two effects with a multiplicative effect, saying that the path length is actually multiplied by a constant k, and an additive effect f, which is really it corresponds to the photons loss. And by correcting those two effects, we are able to come back to the real absorption that we would have measured in transmittance. So in our case, what we proposed was that the moisture content directly influenced the scattering. And so we decided that as there's less moisture content, we know that there's going to be more photons coming back to the detector. And this relationship is actually directly related to moisture content. So we proposed, it was really the intuition that water acts as a guide for photons, and that this relationship actually involved more like a geometrical or volumetric relationship. And so that's why we proposed a hypothesis, which was that the light path length could be directly related to moisture content, thanks to a power law. So we have here L lambda de C, which is equals to L0 times the concentration in water up to a power. And so this is the final law that we proposed here, with still those additive effects which needed to be accounted for. So to validate this law on our simple model system, we needed to remove those additive effects. And to do this, we used the EMSC extended multiplicative scatter correction framework, where we only removed the additive effect. We didn't remove the multiplicative effect. And then once we had this absorbance minus those additive effects, we did a log-log least squares regression to validate the fact that we indeed had this relationship. So here are the spectra that we obtained, measured for the aluminum paper pellets during drying. And we see that we have some differences between spectra, which are simple baselines, and those consist of the additive effects. And when we correct the spectra, we really remove those differences. It's more stable. And also we remove the footprint, the signature of aluminum, our system aluminum paper pellets, which has a given baseline, initial given baseline. So we looked at for one wavelength what kind of evolutions we had. So this is the raw absorbance at one wavelength at 1,450 nanometers. So we see we have those differences from each point for one given water content. Then with the corrected absorbance, we see that we smoothed, in fact, those differences. We removed those additive effects. And finally, when we do a log-log plot, So the log of our corrected absorbance with the log of water content, we see that we have a very good fit of 0.995. And this is interesting because now from the slope and the intercept, we're able to evaluate what is our power and what is the extinction coefficients if we really want to do a spectroscopic study of the sample. So then so this was for one wavelength. We then applied it for all wavelengths independently, each wavelength from 1000 to 2500. And we obtained for most of the wavelengths up over 1350 nanometers, a very good R-squared. And we actually, in fact, had stable, if we look at the slope value, so the power, it was very stable at 1.5. So this further validates the power law. And what's interesting is that we now better understand why even building a simple moisture content prediction model for a wide range of moisture content is actually not suitable. So the PLS eventually can evaluate this power law, but it's linear. So there's no, it's an approximation which could work, but not it's not the best. So we tried to investigate a bit this, what were the implications on those quantitative calibrations. So to do this, we tried to predict water content on our system. So we had X, which were the drying, spectra during drying, and Y, which was the water content. So this is the way today we would actually try to predict the water content. Then we did EMSC additive, so we only removed the additive effects. Then complete is really both additive effects and multiplicative effects. So we remove those path length differences. And finally, what we actually proposed was to remove the additive effects, then do a log-log transform of both X and Y, and look at what we have. So because thanks to the log, we linearize the relationship. And what we can see, so here is the RMSCC of water content, depending on the substrate, the number of latent variables. And even with one latent variable, we have a better model, a more simple model, which means that it's more robust. And so what we see here is that the log transform could actually provide, using this knowledge that we have, could allow building much simpler and better models. But of course, what we can see is that we need to be able to remove those additive effects. And that's, in our system, we had our dry spectra, so we knew how to remove them, but it can be much complex for other systems. So the main conclusions of the three former studies I've presented is that the global linear models were not reliable. The strategy one model for everyone, if we use linear algebra, it doesn't fit. The analysis of water effects, so we see that we have a clear non-linearity, which is depending both on moisture content and the substrate type. And the scattering modifications can be modeled by a simple power law related to path length differences. So from this, we wanted to investigate the possibility of building local models in order to simplify our problem and having a given number of substrates at a given within a given moisture content range, and try to see if we can better build models. So this is my fourth study I'd like to present. So there's the aim was to find a group of substrates which had a homogeneous, which are influenced homogeneously by water effects. So we looked at the principal components, the first principal component, and we actually identified a group of 37 substrates, which indeed followed this power law that we had validated on our aluminum paper pellets. So this is the R-squared that are obtained, more than 0.5 for all of those samples. And so we said, okay, let's use those substrates and try to build a model, since the water effects are more simple to evaluate. Still, there's the non-linear relationship, but at least it's similar. So we build a model on this local group by really using all those substrates and during the drying and trying to predict the BMP. And what we obtain, in fact, is a bad RMSCP of 90, but most importantly, still the R-squared is very low. So we still are not able to build a model, even if we had substrates which, at least from what we see, are similarly have a similar water effect. So the local model still does not provide satisfactory results. So one of then the following question is, can this power law relationship, is it because it's not well modeled by the PLS? Which would mean that we should investigate nonlinear methods to take into account this nonlinear relationship. Or more simply, is it because the biochemical footprint is hidden all the substrates are hidden by water absorption, which would mean that we need to actually reduce the moisture content range. So to do this, we actually try to investigate this on the same local group of samples, so the 37 substrates. We built models with the full range of moisture content, under 60%, under 40, and under 20. And you see that, of course, there's more satisfactory results as you remove the moisture content range, you reduce the moisture content range. So to better actually identify the moisture content range for all the different substrates, what we proposed was actually to use the MCRLS to add the knowledge that we have on the scattering effects within the MCRLS framework in order to better decompose our spectra and try to identify those moisture content ranges. So the principle is really you have X, so the drying experiment, and MCRLS is going to decompose into two matrices of concentration C and spectra S. And with an alternating least squares, you identify S knowing C and X, and then identify C knowing S and X. And what's really great about this framework is that you can add up constraints based on the knowledge that you have on the system. So the spectra here, it's quite classical. We said that the spectra will never be negative. So we added this constraint. And on the concentration profiles, we said that it wouldn't be negative. We said that there's a closure, so we need to have a sum to one of the concentrations. Unimodality means that we have only one mode, so we only have quite simple evolutions of the different spectral footprints. And finally, what's really here new is to add this hard modeling constraint where we force one of the components to follow a power law. So we did this here on wheat chaff. So wheat chaff is really mostly fibers. And so this is the observed spectra that we obtained during drying. And those are the spectra and the concentration evolutions that we obtain. So we see that we have a very good reconstruction with a 1.89 of lack of fit. But what's really interesting is when you look at the concentration profiles, you clearly see here non-linearity up to over 60% of moisture content. So in this case, for this substrate, we would actually reduce. There's no point in building a model from 0 to 80. Linear methods will not be able to do this. So it would be much better to actually do a model between 0 and 60% and eventually 60 to 80. So it also allows to really identify the non-linearities that could be due to measurements, but also just to the phenomena, the substrate specificity. So in terms of conclusions and perspectives, regarding the first objective, which was to develop a better understanding of moisture content effects on nears, and in particular when it's applied to this whole huge diversity of organic materials. So we see that we have developed a new experimental setup that could easily enable us to analyze the water effects and build correction strategies. We see that the moisture content effects were shown to be both physical and chemical, and that we could relate the path lengths differences due to moisture content differences directly with a simple power law. So the second objective, to find new ways of building local models that are robust to moisture content effects. We have shown that the global correction method we've tested quite a lot, they are insufficient due to the non-linearity of effects. That's very clear. And the second result is that the local modeling is actually the strategy that we suggest, and I think it holds promises. So in terms of perspectives, at least on the fundamental knowledge that we have on water effects, I think we should investigate the modified year-long-year law that we proposed in more complex systems, and in particular when we have how to deal when there's an absorption, clear absorption by sugar, by fat, how to deal with those effects, how can they be decomposed, because scattering and absorption are very related, in fact. And so quite similarly, how to remove additive effects. Here we had a simple model where we could remove those effects very easily because we had the dry spectrum. But how can we do that on a substrate where we don't have those dry spectrum? And the quantitative calibrations on wet samples, we want to develop more the knowledge-based local approach that with the help of NCRLS. We would like to evaluate, of course, nonlinear methods, since we see that the phenomena is nonlinear. Can local PLS, SVM, and up to random forest or neural networks, can they deal with this nonlinearity? You know that we are going to have issues, probably. It's more a black box approach, so in terms of maintenance, it could bring issues, but we think it's worth trying. And one of another perspectives could be to use the nearest measurements during drying as one predictor. So I know some authors have done that by heating a sample and taking spectra during heating. And of course, using this this evolution of spectra during a process. So here it was heating, but here it would be drying. Could add up and help to disentangle the different effects and use this kinetic as for prediction also. So this is the use of N-way methods such as NPLS or others. And now in terms of on-site and online applications, we think really the sample preparation and the measurement configuration will be complementary strategies to reduce water effects. And we also should pursue the evaluation of low-cost and handheld spectrometers, so on wet substrates, because this was done during the PhD work on freeze-dried and ground samples. So we see that still we can use handheld spectrometers on those samples, but on wet spectra, we still need to assess this. And with this, I thank you everyone for your attention, and happy to answer your questions.
Wow. Alex, thank you very much for this. This was so brief, and when I think about how you say in your presentation, simple power law, this is so, in my opinion, what you did, so complex, and it is not just, I mean, even to come to this conclusion that it is a simple power law, it is so incredibly complex and amazing. And what you did, it seems to me you have had very short time to just do your research, and from this data that you acquired, you will have, I think, years and years to work on. I hope you will have some help. So now we are, Alex is here. We have lots of questions actually already asked in the chat box, and me, Pierre, and some other people commented so far. Okay. But if you can take a look in the chat box, we can start from there. If anyone has a question, please just raise a hand, and then moderator will give you a word when Alex answers. Okay.
Okay. So I'll start with the first questions. So I think there was one from Pierre. Have you tried to use BMP approach without the freeze drying procedure? And if so, what kind of results did you obtain? So I think that was at the start of the presentation, because so I presented in the first chapter. Basically, when we applied we tried to train BMP prediction models on both freeze-dried and wet samples, we double the error, basically, or triple, it depends. But what we today want to try is actually to, as I was mentioning in the conclusions, is to try some non-linear methods, because currently what has been tested is only on global linear models, and as we've seen, the problem here appears to be very nonlinear. So we would like to try some more, unfortunately, black box methods, at least for the application. Yeah. So then, Yelena, you were asking, how do you define moisture?
Yes.
So, complex questions. Actually, here we defined it just as it's the opposite of the dry matter as it's measured. So we just take the weight, the initial weight, the wet weight, and then we dry the sample, and we have a dry weight, and you do the difference divided by the weight, the wet weight, and you have your moisture content. But what's true is that when you dry like that, you have the volatile fraction. So for example, the volatile fatty acids, which can escape, and those are organic matter, but it's difficult to evaluate this volatilization.
And also, so I never thought about that fraction, but yes, of course. Although I think it influences less than, let's say, this effect than the water, which cannot be lost to evaporation, because you can only. So this is why I say usually when I say moisture in my head, it is just the water that can be evaporated. So there is a type of water which cannot be evaporated by drying, which is bound to this substrate. So that is why when you're removing moisture effects, you're basically just removing the effects of this, I think, gaseous phase of water.
Okay. Yeah.
But there is.
Usually you have like the free water which evaporates very simply. Maybe it depends on the substrate, of course, but using drying, you still remove the bound water, but of course you go up to maybe 99% of moisture content of dry matter, and there's still this 1, 2, 3% of water, which is really bound to the water, the substrate, and cannot be evaporated. And when you get it out from the freeze dryer, maybe coming out from the freeze dryer, you're at 99% of dry matter, but it rehydrates and goes back to maybe 95 or 96%, depending of if it's. I think of like cellulose and paper really rehydrates very quickly. So
this is we have a chat, one question in the chat box from Professor Petrucci. He just asked the question regarding this. Have you tried to analyze the kinetics for the adsorption and or hydration of the samples? So this is exactly what you just were mentioning.
So in fact, we didn't. So at first, before the PhD work, we had tried to do. We actually took some samples which were freeze dried and we rehydrated them. So we added water instead of here. I dried and then I followed the kinetics. The first step was in fact to rehydrate because it was more simple to set up as an experiment. But for the application, what we wanted is actually to be able to measure the raw substrate. And we think like if you take a salad, if you dry it and then rehydrate it, you won't have a salad at the end
anymore.
So it meant for us it was more meaningful to have the sample as its raw state and then dry it to have all the water effects that you can have. But yeah, it's Pierre, you're mentioning the hysteresis effect. That's exactly it. So
I'm sorry, we have again a raised hand. Professor Tsenkova, can you please unmute and turn on the video?
Yeah, Alex, thank you. Can you hear me?
Yes.
Thank you very much for the wonderful talk and of course work. It is very, very deep and wide. And I think you have just scratched just a little bit. You have just started.
For sure.
And I have an idea that maybe you would like to follow in the future. The first thing that probably you need to do is to see how the spectra of the water changes when you start evaporating it. Have you done this? Simple water, not a substrate.
Just water when you,
yes.
Okay. So
yes.
in fact, I took measurements with the system with just water and starting to dehydrate it. But it's not suitable because I take it with reflectance. And so, in fact, I think I need to have a really thin layer of water to dehydrate it. Otherwise, when I dehydrate it, it's just the top of it that dehydrates. But in fact, the spectra is just the same because it's a very small
I don't think
layer.
so. The spectra will change. But yeah, you better look at the transmittance.
Yeah, it's in transmittance, but in terms of experimental setup, it's quite sketchy how to do that.
No, I don't think the water changes only on the surface. If water changes on the surface, it will change also in the whole volume in the cuvette. So
well, yeah, maybe it's just yeah. In terms of experimental measurements, I don't know how that could be done.
Well, we can discuss this, but just have it in mind because I think it is your control to start with, and also especially for the power law. So when you want to correct, you have to start with the knowledge about the evaporation of the water and how the absorbance of water changes and does it fit your equation. Yeah, thank you.
Yeah, it's true that here the law was validated really on a sample where you have solid particles in suspension. So how it would be dealt when it's just pure water and liquid, I don't know. This is still remains a question. Yeah.
Remember that water, when you evaporate water, it will restructure. And it will restructure in a way, making new structures with different sizes also that might be comparable with the wavelength. So you might have scatter also in the water. Yeah. Okay.
Interesting.
Thank you.
Thank you.
Other raised hands? Are there any?
Pierre was talking about.
Tanaka Hideo-san had a raised hand.
Hideo-san.
Tanaka Hideo-san.
Okay. Yes. So Masa. Yes. Recently, we published the hydration of inorganic material follows a second-order reaction, but the absorption of H2O onto the surface does not. I guess that's one important viewpoint. Maybe you can explain a little bit more, Masato.
Takeuchi-sensei. Takeuchi-sensei.
Takushi-sensei, sorry. Maybe you don't have access to the micro. Okay.
Takeuchi-sensei, can you?
Okay.
Yes, please.
Hello.
So we were talking about your question. Can you just repeat and say a little bit more?
Yes. In slide 46, maybe you observed the NIR spectra of water depending on the relative humidity.
Yes.
Moisture concentration.
Yes.
I think you can fix the relative humidity and the spectra depending on the adsorption time. You can obtain the NIR spectra depending on the time when you expose the sample to the moisture.
Yes.
So the adsorption water increase. So you can analyze the kinetics of the adsorption constant.
Okay, and it's a second order reaction. Okay.
Yes.
Well,
so important point is the first order or second order or something different phenomena happen.
okay.
Sometimes it's difficult to analyze the kinetics of hydration or adsorption. But I am very interested for that phenomenon.
Yeah, it's very actually it's quite similarly to that. We identified during the drying we identified different phases in terms of dehydration speed. Because that's a way that's used today to to identify the free water, bond water, and inside the bond water phase you can look at different sub phenomena. And maybe I can share my screen. Wait.
Yes, please, that would be good.
Écran partagé.
From slide 46, maybe.
Yes, actually I was going, so 46. No.
Yes.
Yes. So you were mentioning maybe this blue line would follow actually a second order reaction. I was going to just show you another slide here that I had in mind. So maybe I will share it. Can you see the screen well? Yeah.
Yes.
Yes.
Okay. So just quickly in blue, this is the wait, let me think of it. This is the loss on drying. So it's the amount of water that was lost during the drying. And in orange, this is the derivative. So the first derivative of this curve. And so those are called the Krischer curves. So that's what I was mentioning. It's to know like the drying speed during the drying experiment. So we look at the orange curves. And usually when they use those curves, it's mainly in food science. They identify the different phases of the drying. The drying speed, and in theory you have a first phase which is warming of the sample. Then you have a constant drying, which means that it's really free water that's evaporating. And then you have a drying, a decreasing rate. And that's where you enter the bound water phase. But it seems that on food, free water is rarely observed because you never have water just at the surface, which is that free. So and this is what we can see in most of the samples, you always have a decrease. Maybe here for like wheat chaff, the first phase here, you have free water because this was wheat chaff that was mixed with water. So you have a free water phase. So wheat chaff is really made of lignin and cellulose. So it's very, it doesn't interact much with water. And the second step could be actually divided in several regimes related to structure. So the cell wall that changes, the pores, the hardening, the different phenomena. But it seems here in my data set, I couldn't identify easily those phases where you have within the bond water, different phases of different types of water. So
I actually think I saw that in your results. Can you go to the when you approximate the when you go to smooth the curve and then you approximate it with the very nice power law. Oh yeah. 36 slide 36.
Yes.
So you see, when you put the line, you when you put the linear line on the third graph, you don't have actually, you have waves.
Yes, you have
so I think this is a very systematic to say that in my view, this is too systematic to represent a random, like error of so it is very, I agree, it is a very low error, but I still think that it is very systematic, and I love these waves. We very often see these wavy-like structures in different processes, like illumination of, for example, I saw just today in gel, let's say when you illuminate it, irradiate it with light consecutively, you have that pattern like wavy, it becomes wavy. So it's just like, and what we hear regardless what you said, I really think that the building local models on everything is just the best way. So here, I also think that you just, even though this is, I still think this is too global, and I think that you with this smoothing, you underestimated or actually pushed aside a little bit one part of information that I think is very, very important for the really behavior of water in your substrates. And this is especially around this 38% of water content when you have a sharp breaking point. This is what I'm thinking, for example. And it's also around between 20 and 30%. You also have this like, it is not ideal curve. So I think that at this point is what is happening, what Takeuchi Sensei was talking about. We have this absorption, and then we have hydrate. I really think that this absorption here is switching to something else.
I think maybe the approach would be that maybe the next steps regarding this experiment should be that we should take more and more samples with the system and have a lot of replicates and start having to really know whether those variations are significant or from what phenomena do they come from. But possibly if they repeat, there could be an explanation regarding different phases. Maybe the model is too simple, in fact, and too global, but I think in order to investigate this, we should have maybe take more measurements on different systems.
Yes, sorry, Pierre has a question. Pierre, please.
Okay, can you hear me?
Yes.
Yes, very well.
Okay. Merci beaucoup, Alex. This was very, very deep stuff, and I'm very impressed about the achievements that you have done. And since you already opened up this particular slide 36, look at the very right graph, the log-log plot.
Yes.
I mean, have you ever wondered why this linearity pops up suddenly? Do you have any clues why this is so straight?
Well, this is still, I think we still need to investigate and find a good interpretation of this, because currently it's more an intuition, as I was presenting, more like saying that the more and more there is water, the more there's scattering, forward scattering, and the more there's a probability that water molecules absorb the light. That's how I see it. But it's as I know, like power laws are in a lot of natural phenomena, and they can be related to fractals and to but here I still miss, for me it's more like a geometrical relationship, just as path lengths can, like a distance related to the volume, could be that sort of relationship.
But you mentioned now a key word, which is fractality. I mean, fractality in that case, I think, is the basic underlying denominator. Because what I see, if I just look at it, it means that if you lose water fractions, you lose it in a very distinct manner, which means that allows you to, let's say, you can even term it as quantized states. It's not the appropriate terminology, but it's some like that's in discrete portions you lose the water. And it's like in a harmonically structured way. And in such a, let's say, dehydration process, you can literally see the coherent fraction of the bound water fraction that is detached from the absorbed material into the gaseous phase. However, it maintains its coherence. And this is what I read out of this particular graph.
Okay, well,
I'm not quite sure whether I was too complex or too complicated.
No, I think I'm not very familiar with the coherence phenomena and quantum maybe physics, but and I'm not an expert on fractality at all, so maybe
well, let's not make it too complex. The fractality property here only states that you have a self-similar, let's say, behavior of how water condenses onto the substrate and, let's say, detaches again during the dehydration process, which means it is a kind of water ordering functionality. Let it aside whether this is induced by the solid fraction, that is where it is absorbed onto, or it is a property that is intrinsically, let's say, written into the water matrix. It's only there that you can see the fractality is a kind of a mirror of the coherently allocated, let's say, oscillation patterns that you find in water. This is, for me, let's say, the underlying denominator and the crucial, very crucial function that you need in order to maintain the substrate biologically viable. Otherwise, we can probably talk about inorganic materials that are not biological functionality, that don't have a biological functionality.
So in this case, you wouldn't link it to physical effects related to scattering?
Not really. I think it's a real phenomenon that you observe during the dehydration process that is related to the water that you measure, and it's not an artifact.
Absolutely more than that. You will, Alex, I think you will, in the next few years, understand that you discovered here very, very big stuff. Pierre is trying to actually. So Pierre will also talk about this coherence in the next webinar. So maybe it will get you know, more structure in your head.
Some more notions on, Okay.
Can you tell me, just because you mentioned about the power laws, you mentioned that you had substrates that didn't follow this power law.
Yes, it's
which substrates?
Those are the mostly sample. The good examples can be found like when I was talking. Wait, let me see. Yes, the obvious samples are the samples which have a lot of fat inside. So pork, sour cream, butter. They have really the opposite evolution. They don't have a decrease of absorption along the drying, but they have an increase actually. So those samples didn't work out. And another type of samples was like samples where you had at some point a sort of saturation of the signal. So it's not a like spectroscopic saturation. It's just that in all wavelengths, most of the photons scatter. And so you can't make a difference between one wavelength and the other in terms of absorption, really. So it just appears like a flat. So sugar, lactulose, brown sugar, fish, those are samples which at some point we did not follow the law. But if you look at, like, for example, soy sauce here in red, you could say that up to 30% of moisture content, you still have this power law that could be, so.
It's interesting that this unhealthy food doesn't follow.
Not that soy sauce is healthy food, no?
Thank you. That's too bad. I really like mayonnaise. I think Professor Tsenkwa mentioned that there was one more raised hand that I missed to see on time.
Yes.
Can a person? Yes. Oh yes. Takeuchi Sensei.
Drying rates. Sorry.
Depend absolutely on viscosity of liquids. Absolutely.
Yes, the drying rates complete. Yeah, they depend. As I was mentioning, like in the bond phase, usually you can have a lot of different physical phenomena that modifies those drying rates. You can have crusting, you can have contractions. Drying is actually a very complex phenomena, and actually that could be one of the that's one of my, I think, in terms of progression around thinking about this subject, the fact that physical effects have a big importance actually in terms of in the water effect. So during drying, you have a lot of different phenomena, and this changes the physics. Water content is it's not just a chemical effect where we say, oh, water absorbs too much. It's also, oh, water absorbs too much, but you also have water that disturbs and changes the physical state of your matter. So this completely changes the near infrared spectra that you measure.
Pierre, I have to then ask us, because, okay, we are all water scientists here participate. So Pierre now said something which I hate when I hear this word, because nobody ever explained to me very nicely. What is bulk water? Can you tell me? What is bulk?
Bulk. I'm sorry.
Yes.
I just typed it in like this because Professor Takeuchi just inspired me to give this kind of response. Bulk water. You have from the framework of quantum electrodynamics, we can consider water as a biphasic entity. Mm-hmm. You have bulk water, which is just water in, let's say, that follows the KT, the distortion, which is the Boltzmann thermal energy input from the second law of thermodynamics. Which means it's just disordered. It's kind of chaotically, almost stochastically disordered water molecules flipping around and building up and breaking up hydrogen bonds in a very flickering manner. So it's in a disordered state. And there's no correlation whatsoever in terms of phases. Which in phases, when I speak of phases, it's like, I'm not quite sure whether you can see my hands. Can you see my hands?
No,
yeah.
Up.
More towards your...
Good.
Yeah. Okay, these are the water molecules with their dipole moments, and in a bulk water phase, you can speak of these molecules are flickering around like this, and they only have very brief interaction with neighboring molecules in femto and picoseconds framework timescales. However, when you look at the non-bulk, so the coherent phase, which is then the flipping of the oscillations from the chaotic stage into an ordered stage, these oscillations begin to kind of stabilize itself in such a way as they start to dance in a chorus, in a kind of a ballet. Their phases, they become to align. The phase difference tends to become zero. This is the coherent phase. Whereas in the bulk water phase, the phases, they're non-zero. They're far apart. So does this explain your question?
Yes, because I'm very often told, so first, in some papers, I see free water molecules are bulk water, which in my opinion is not the case. Then from other people I hear, bulk water, that's small water clusters with just few hydrogen bonds, which I also was not. And now what you said definitely agrees with something I always notice. And there are, of course, in some papers, this assignment of in near infrared, it is 1450, the exact band that Alex showed. So 1450 is actually, around 1450 is this totally, I don't see this coherence actually.
Well, you should also keep in mind that when you speak about the bulk water phase, it's an energetically activated space because it suffers from, or it's under the influence of the thermodynamic perturbations, which means it's not a really ground state. It's a perturbative ground state. It's slightly elevated, whereas the coherent state is, because of the coherent coupling among the water molecules, is less energetic. It's a kind of a lower state, and that's why it's so stable. But maybe we can talk about this next time, and it's because then we go directly a little bit away from that what Alex was talking about.
Sorry, it's fine. I just want one more thing, because for me it's 1450, the exact band that I told now, like a bulk water, is also what I see as physically absorbed water. So that is why I'm not. It is very of practical importance for me. This is also what I see, that it is most, how can I say, it is the first water that it is lost on drying, on temperature, on autoclaving, on so this is the first that attaches to surface, first to detach from the surface. 1450 nanometers. I can't say about the structure, but I just see it as a band, as an energy.
Can I enter a little bit?
Yes, please.
Yeah, thank you very much.
Thank you. Sorry about that, Romeo. Go ahead.
I just wanted to say that what you said, you're talking about frequency of vibration, and it depends very much on the energy.
Yep.
So, beautiful slide we saw, where we have coherence above kind of 1300 nanometers, and then we don't have coherence below. And below is an area of high energy already. So we have electron transitions visible, and then, so it is very difficult to define what bulk water is, but probably it relates to the energy of vibration.
Yes, it does. Surely it does. And you should see the energy difference in the spectra.
Yes. So we still have way to go, I think.
I think it would be very good. I think, Alex, it would be very good if you give, if you put this on some kind of, I mean, your presentation on some kind of forum. We have a forum, but it is not very functional on our website. So everyone can come and put comments, so we can basically work together on figuring out your data and what it means for each of us in the terms of coherence or I don't know, scattering, absorption phenomena. I think it would be really great to have that kind of joint work, if you can, of course, share.
Yeah. It's just like the open science initiatives where you publish something and then you have the community that just comments, suggests, and then you need to answer. It's the reviewing process of the open reviewing process that there are a lot of initiatives like that in
well,
science.
maybe we should, I think we should do something. I love your work. I love
Thank you. Yeah.
What I see now from Takeuchi Sensei again. He says, and if the sample contains solid specimen like porous materials, the absorption rates are affected, which is really connected with something we worked, but with food. This porosity of food actually is, if you have pores inside the food, that it means you have increased surface within the food. And so this surface means more active surface to interact with water available. So it's so important on so many levels. I wish I could understand it better. I'm again talking too much. I'm sorry. Anyone has maybe any question apart from me?
Look into the questions that we missed.
Yes, absorption and desorption. We have one possibly postdoc next year, which would like to research exactly this phenomena in food, absorption and desorption. Actually, hydration and rehydration and the relationship with water activity. It's quite nice.
Yeah, I think there are things to explore actually in terms of the link between the near-infrared spectra and the water activity of the water types. Here, that's actually what I wanted to study through this work with having with a lot of substrates. But that's the difficulty about the here was that you have so many substrates that trying to investigate the water types in those substrates was quite tricky, and there were too many physical differences between the substrates that it was difficult to distinguish those differences in terms of water structure, at least for
now.
Yeah. So I think like within one substrate, you can dive into explore the water structure, but it was quite difficult with all those substrates together.
Alex,
yes.
May I just briefly add another question, since there's a time slot available and nobody else is taking it. It's regarding the hysteresis that you briefly mentioned before.
Yes.
During the hydration and dehydration process, I suppose if you dive deeper into this particular phenomenon, you might be able to exactly extract the energetic quantity of how much energy is required during how much, let's say, the cooling effect and the warming effect. The cooling effect during dehydration, the warming effect during the absorption of the water onto the substrate. And then calculate the energetic equivalent, because this could be also an indicator of how much of the energy is required, and then related to the classical thermodynamic principles and then to the quantum electrodynamic approach, which probably I postulate you are most likely to see something that points towards the electrodynamic property, which means you obtain an energetic lower state than that what you expect when you just look at the thermodynamic aspects.
Okay. We had issue, like we thought of rehydrating using the experimental setup, but it's in fact it wasn't adapted. Here we built the experimental setup so that it could dry and take sample spectra automatically. But for rehydrating, and so that it's uniformly rehydrated, that was a little bit more tricky. So we have to think of the experimental setup, but I think, yeah, studying both dehydration then rehydration could help to disentangle the different effects and better understand.
This would point directly to a particular phenomenon that needs to be looked at. And I've just seen that Professor Takeuchi came up with a literature suggestion. So I need to have an access to this paper.
Yes, we should.
Let's just check it. So I'll shut down briefly.
I just want to announce, please, so we should be wrapping up, unfortunately. So I just want to announce we are going to now do a poll. So everyone should have at their windows just a little bit, a short questionnaire to fill in with 3 questions. So please, just don't, your opinion your opinion is very important. We would like to know what you thought about the webinar, and if you have ideas for the next webinar, or if also feel free to comment if you want. So Lawrence, can we have the poll? Okay, poll should be now. Do you see him? Do we have a poll? No? Everyone has. Okay. I really like what you. Unfortunately we did not have this time to discuss this, but I also liked that you said you investigated different types of spectroscopy and the influence of polarization. which is something that I did not see today. People from New Zealand, but they have different results. Recently, they showed some things interesting when they use polarized light and when they use non-polarized light. So this was also something that I captured my attention. Maybe we could have one more webinar with you.
Which team was that, Yelena? Just it. Which team analyzed the
from New Zealand?
Okay.
From New Zealand, they will have very soon a paper published on that in our special issue, and so I also liked, but we did not the handheld spectrometers. You used the portable. It looked to me as if you had a FTIR gun. Was that the instrument that you used?
We used different ones, but the really tiny one that we used was the Neo Spectra. It's like a small one, which is from the Cyware company, Neo Spectra, which is a MEMS, so Michelson micro-electronic device, where it's an FT NIR microspectrometer with a wide. What interested us was that it was a wide range. Actually, we have a paper where we compared the performance between the dry and the different spectrometers and different measurement modes. So we used actually polarized light. So I can. Maybe I will share the ref somewhere. Maybe wait.
Please just if you can put in the chat. Okay. Can you find?
Maybe
that's very interesting. That is such a novel thing about the polarized light.
But it was on dry samples, huh? So.
Nothing is totally dry. Nothing. You cannot isolate. I think.
I will find me up. Yes, this one. Oop. Okay. Thank you. Don't hesitate if you want to discuss about the results.
Did you send it in the chat box?
Oh, I send it.
To just one person.
To Masato, Takuchi-san.
Sorry. Thank you. Lovely. Great. Fast. Very soon. How come I don't know? Thank you, Alex.
You're welcome.
All right. We have time for one last question for Alex. Is there someone who would like to ask something? Professor Tenkova, any final questions?
No, I don't have questions. It is such a vast area, but I'm happy that we started. And I was very happy to have Alex in our lab.
We still miss you.
I miss you too.
But I think this discussion today also is a good driving force for the future, and it's a big. It is very important biotechnology, and from now on, what you're doing is so important, and so many people will want to do, and to get some energy out of this waste. And you have to develop a very, very good technology. So I think all the knowledge that we have more and more in aquaphotomics are helping this process, because we know more and more about water structure and the changes with different perturbations. So I wish you good luck, and it really there are many people waiting for the results and how to really use your studies. Good luck.
Thank you.
Thank you.
Okay, I think Professor Tenko, we mentioned once that Tanaka-san had a question. Hideo Tanaka is.
Yes, I saw.
Are there any?
But I don't see him now.
I see that, yes, I was monitoring to find, and I see a picture here, but I'm not sure whether Tanaka-san is here. I apologize for not spotting at the time when the hand was raised.
Thank you very much, Elena, for leading the webinar very nicely, and Pierre being so active. So
yes, Pierre, it was very nice to see you. I didn't think you would manage to come. It was beautiful to have a discussion with you, although again short.
Pierre, can I ask you? Are you with us?
Yeah. Go ahead.
You will help us a lot if we can record your talk, so we can.
Sure, no problem.
We can do a little bit better on the Japanese translation next time.
Mm-hmm.
And people will be very happy having Japanese as well. So if you can help us, it will be great. So we don't have much time, but we'll try. Yeah,
well, I will.
Oh, it can go a raw Japanese.
I already decided to trim it down because today I realized that Alex had roughly about 50 slides, which is, I think, feasible, and I need to trim it down anyway. So rather than covering the full section that I intended to do last time, I will only pick raisins, and maybe we have the time to stay and stick to certain issues and talk about these, which is probably much more beneficial to everyone. And then we don't need to rush through translations, but we can take our time.
Okay. And then we can, with this technology already, so we can have part 1 and part 2 and part 3, and people might be very interested in what we're talking. So we'll see the unheads today, and we'll see next time also. I think it's a good start. Yeah. Thank you.
Great. Yep. Thank you.
Okay, so then for just the last thing to do during webinar, we said that we're giving away 2 books, one this webinar, the second one next webinar. So this time we took all your numbers, because when you signed up, you were given a number, and now we randomly selected one number, and it was 66, and number 66 signed up person is Ahmad Fairuz Omar from University Sans Malaysia. Fairuz, are you there? Well, anyway, if you're not there to say, he is here. He just is in chat box. So Fairuz, this is our Christmas present to you. Just please write to us to tell me an address to which we can send the book. And it will be very, very big pleasure for us to introduce more aquaphotomics in Malaysia. Malaysia has a very, very good team which is contributing to aquaphotomics recently very much. So I hope this can lead to even more progress. That would be wonderful.
Congratulations.
Congratulations. So thank you very much, all of you, for attending. Alex, thank you very much for this lecture. I felt again that it was too short. You have to come. You have to come. I think again to our lab, and so we can work on this more. Well, stay with us for the next webinar. So that is next week, 22nd of December, at the same time. I hope the time is nice for European people. I'm not sure how is it for USA people, but in Japan it is quite nice. We're wrapping up a day. And so then next time, Pierre Madel, Dr. Pierre Madel, who nicely participated in discussion this evening, will be talking more about coherence. So I hope to see you all at the next webinar. Yes, Pierre.
Just a brief question. I'm trying to copy the content of the chat.
Okay.
Protocol. Is there a way how to get this copied on the clipboard?
Yes, I think so. Lawrence, can you have chat saved, and we can do that for participants.
Because I only get the sections, always only a section.
Yes,
not the full discussion.
Pierre, I think in the chat you have those 3 dots on the right next to the
dots on the right.
Yeah.
Yep.
And you there's like save the discussion normally.
Save chat.
Save chat. So hold on a second.
Chat save.
Want me to share my screen?
Yeah, go ahead, please. It doesn't work.
So wait. When I share my screen, yeah, no. So discussion. Here, there's those 2 dots.
I only see your PowerPoint. Oh, okay.
Here, 3 dots, and save the discussion or the chat. Can you see that?
No, I don't. I just see your PowerPoint presentation. Sorry.
Pierre,
okay.
I will give. I did what Alex said, and I ended up with the chat, and I will now put it.
Send it to me. Okay. Perfect. Lovely.
Yes.
Thank you so much. Sorry.
Okay. And one final thing that I forgot to tell, but luckily I remembered. So starting from today, all our conference videos are available on our Aquaphotomics YouTube channel, so you can have all presentation videos there, including Alex's presentation and Pierre's presentations, including workshops and everything with Japanese live interpretation.
Jelena, I shared the graph with the participants.
Oh, lovely.
Yeah, I think everybody can see that. Can you see it now?
Yes, we see.
Okay. Well, this is what we have now.
Today, yes.
Nice.
Okay. So my computer was a little bit problematic now.
So we had lots of people from Japan and China.
Yes. Thank you.
Well, this is now the end of the first part of the Aquaphotomics Christmas special webinar. Thank you all for coming and participating, and I'm looking very much forward to seeing you next week with Pierre Model. Many greetings to all of you from Japan. Thank you, Professor Takeuchi.
Thank you so much.
Thank you, Alex.
Thank you.
Thank you,
for the
Pierre.
organization.
Thanks. Thank you so much.
Serbia do Tokyo.
Thank you.
Thank you, Professor Atanasov. Thank you, Brim.
Oh.
Thank you, Yonosato Lab.
Hori sensei, Hori.
Thank you, Balki.
堀場です。ありがとうございます。
Thank you, Zoltan's Lab. See you next week.
Brim. Hello, Brim. Thank you.
Hello, Professor. This was lovely.
Good. Yeah. So good to see you.
Yeah, good to see you too.
Wonderful.
Okay, 5, 4, 3, 2, 1. Bye.
Bye-bye.